having sadly the last lecture.
Thank you. All right, ready for the finale. Let's hope. All right, so I'm gonna start from where I left yesterday. So we were discussing the clustering of galaxies, and again I emphasize, when I'm saying galaxies, it can be any tracer that is out there in the universe, and we'll talk about some examples later when I show my slides. And we are we are writing the most general relationship we can think of based on the two symmetries in the problem. So we have Galilean invariance. You can always change your frame of reference by shifting the velocity by a constant. This must be a symmetry. Remember, the velocity is the gradient of a potential. So the potential changing, the gradient of a potential changing by a constant, for that to be a symmetry means that the velocity potential can appear with at least two derivatives, okay? So we need at least two derivatives acting on each velocity potential. The other symmetry in the problem is the equivalence principle, which is the symmetry, the gauge symmetry, the symmetry that remains from GR once you are at small scales compared to the Hubble radius. Similarly, the principle of equivalence says I can jump into the Einstein elevator being free fall. The physics should be the same. Accelerations changing by a constant by going, say, into the free falling frame by making your acceleration 0 at a particular point in space must be a symmetry. This is just the gradient of the gravitational potential changing by a constant must be a symmetry. Again, that means we need to have at least two derivatives, okay? And so remember these guys, then we are dealing with scalar fluctuations, both in density and the tracer we are looking at. And so we are writing the most general relationship that we can write out of scalars that you can make from these second derivative fields. So the most obvious scalar to make of these guys is the trace. We already know these guys, right? Again, you can scale this by constants, so forget about the, I'm not putting a constant of proportionality here. So the Laplacian of phi is delta, the density perturbation. The Laplacian of phi v is the velocity perturbation. And remember, these two guys agree in linear theory, so they only differ at quadratic order, okay? So at linear order, the only thing you can write is, since these two guys are the same, let's write everything in terms of delta. A linear order, that's a single coefficient. That's what we call the linear bias parameter. At quadratic order, things get more interesting. You can now do the square of the trace, and then you can build this other scalar from the tensor of second derivatives, okay? And that's all that you can do, right? Because if you do the same for the velocity potential, because at linear order they are the same, and this is already quadratic, they will only differ at cubic order. And so we'll have two parameters, the quadratic bias, and this is called the tidal bias, because this guy measures tidal fields, and so on, okay? So I'm not going to explain everything that I did last time. And so at cubic order, in order to do the one loop power spectrum, we need to go to cubic order. So that's what I wrote. That's where we stopped yesterday, okay? So I'm not writing here. This third Galilean has a long expression that I wrote yesterday. I'm not going to write it again. Okay, so now remember, this assumes this assumes, as I was saying, that we are looking at scale. So as we'll see later, galaxies form inside virialized systems, which are these dark matter halos, okay? And so we are looking, so if the size of a halo is R star, right, we are interested in scales which are much larger than the size of a virialized system, okay? And so we are using perturbation theory, and in that in that scheme, right, we know that quadratic fluctuations are smaller than linear, cubic and smaller than quadratic, and so on. So we have a hierarchy of corrections that is well established, okay? And so to write this relationship, notice we wrote everything at a single point. So we are assuming that the formation of galaxies is essentially local because we are looking at scales much larger over the size of the dark matter halo, of the size of the patch out of which perturbations collapse, right? Now, in order to be more general, to go beyond locality, we want to include the fact that when you collapse to form a galaxy, you are grabbing matter from some region, from this R-star region, essentially, and collapse. So that means, to be most general, we should smooth this thing over this scale, right? But because we are interested in such a longer scales compared to this, or in other words, this is much smaller than 1, we can essentially do a Taylor expansion or a derivative expansion of this smoothing operator, or this smoothing operation on these guys. And so all that does is the fact that we are grabbing matter from some distance r star away is to include, to lead in order, will include terms which will go, say, for this operator, which is the first one we had to worry about, you will include corrections that are essentially k squared r star squared delta, okay? And so that will include, this is what we call higher derivative bias. And so this effect will now feature here as a new parameter here, okay? Which has to do with the fact that now it's not exactly local, but we are smoothing on this scale, okay? And so that will include, for example, the smoothing of this operator now will include some new parameter here, which is related to this R star, okay? So that sort of completes our basis of operators in which we write fluctuations of any tracer as a function of what's going on in the dark matter, okay? And as I say, this is so general based on symmetries, right? And the perturbative expansion that is true for any tracer of dark matter as long as the symmetries are respected. So now what I'm gonna do is we're gonna take this and calculate correlation functions of delta G, okay? Which at the end is the observable we are interested in. So I'm gonna, as you can imagine, so these guys are nonlinear fields, right? Remember, delta has all these nonlinear corrections, right? So this can get pretty ugly pretty quickly. So I'm gonna do 2 applications. So first I'm gonna do the non-Gaussianity. And then I'm gonna do the one loop power spectrum schematically because there are many terms, but. So let's start from the simplest. Before I do the one loop power spectrum, let's do the linear power spectrum, which is 3-level. So this is trivial, right? Because to do the linear power spectrum, you just use linear theory. So the only thing you need to do is just multiply by B1 your density fluctuations. So this one is straightforward. So I'm gonna denote by GG a power spectrum of galaxies against themselves. So it's just an overall constant times the matter power spectrum that we already computed in linear theory. So this is trivial, right? So it's the same thing that we have with the scale factor for the time evolution. We multiply by an overall function of time. Now we are multiplying by an overall constant. And this constant will depend on the type of galaxy that you're looking at, okay? So it's not something we can predict, unlike the growth factor. So if the linear power spectrum goes essentially, remember, AS k to the ns times the transfer function square. Sorry, my writing is becoming horrible. And then we have the growth factor there. Right? So if we say, okay, this is roughly some amplitude, right? Some k to the n effective that depends on k. So there is some overall amplitude, right? Which is related to the primordial amplitude coming from inflation and the growth factor up to the redshift that you're looking at. So you see this thing scales as B1 times that amplitude square, right? So this kind of scaling will be useful to see how non-Gaussianity will break some degeneracies and so on. Okay, so let's keep that in mind. Okay, so now let's do the three-level bispectrum. So for the tri-level bispectrum, remember when we did the gravitational one, we had to include up to quadratic nonlinearities, right, in this guy. Now you see there is also quadratic bias. So the relationship, when you go from delta to your tracer fluctuations, that relationship is also nonlinear. So even if this guy was fully Gaussian, which we know when we evolve it is not, as you go to your tracer, you create new non-Gaussianity because this relationship is nonlinear. By the same calculation that we did when we went from linear fluctuations to nonlinear fluctuations in the matter through gravitational evolution, now we have an extra source of nonlinearity, which are these quadratic corrections, which is all we need at 3 levels. Okay? So this will enter at 1 loop in the bispectrum. So it's the same calculation we did yesterday yesterday. I've already lost track of what I did each day, but I did it yesterday or the day before yesterday. So we are going to get, you can do the same calculation that we did. So let's do first the linear term. The linear term is trivial, right? The bispectrum of this is B1 cubed times the bispectrum of that. Just because I had to put 3 delta G's, I will get 3 delta 1s if everything else is ignored. So this guy is just saying the first term. Okay, I'm not putting the arguments, K1, K2, and K3. I'm not. So if all there was linear bias, the non-Gaussianity we see in galaxies will be exactly the same non-Gaussianity we will see in matter amplified by this B1 cubed. Okay? Is that clear? So that part is straightforward. But then this nonlinearity will create an additional bispectrum, right? Because now if I take here the linear fields, this is a quadratic nonlinearity, right? And so it will, when you do, say, this cube, it will be, there is one term which is 3 times this square times this. And if this is quadratic with this square, gives you a non-trivial 4-point function for a Gaussian field, and then you calculate. So if you do the calculation following exactly what we did with the nonlinearity, you get 2 terms, one proportional to quadratic bias B2, and the other one proportional to this tidal bias gamma 2. With a kernel that depends on the kernel of this G2, which is this, right? Which we can write in Fourier space in the usual way, the same way we wrote the F2 kernel in terms of the linear density perturbations. And so this is an integral over K1 and K2. Okay, so this in Fourier space, K. And that kernel capital K is very simple. It's just, again, it's a scalar function of the angles. So it's the cosine square of the 2-way vectors, okay? So you can show it from here. That's an exercise. Okay? So that means that will appear here in the bispectrum. So we get a new dependence on triangle shape. Okay, and again, there is cyclic permutations over K1, K2, and K3. So 3 terms here, 3 terms there. Okay? So now I can use the expression that we have for this guy in terms of the F2 kernel and put everything together. So I have this F2 kernel that comes from this guy, right? Multiplied by B1 cubed. Then I have B2, B1 square. Then I have 2 gamma 2 B1 square times this kernel. Everything times P of K1 of the matter, P of K2, plus cyclic permutations. Now, because the power spectrum to leading order is just B1 square, I'm going to absorb a B1 to the 4th to make these two guys the power spectrum that I measure. So I'm going to multiply by B1 square each of them. So this will become PGG of K1, PGG of K2, and then I have to divide by B1 to the 4th, the square bracket. Okay, and that's my result. Okay, so there are 3 terms like this, where you have here you have K1 and K2, then you have K2 and K3, and then K3 and K1. Okay. Now remember, this guy depends on the angle between K1 and K2 through this kernel that we discussed, right? There is a monopole, which is the spherical collapse dynamics. There is a dipole, which is the shift, okay, as you go from initial location, the perturbation moves, right? And then there is a quadrupole, which is due to tides, right, which deforms the shape of structures, okay? You see the quadratic bias contributes, again, a monopole, right? And this guy contributes, again, something that is also related to the tides, okay, which is this structure, okay? So you can see now how things can get interesting in terms of breaking the degeneracies, right? Because when we measure the power spectrum only, there is a degeneracy between the amplitude of the power spectrum that has all this cosmological information we care about, right? And this bias, which is some accident of what galaxies we are looking at, right? We cannot disentangle these 2 parameters, right? So now here, for a fixed amplitude of PGG, which is what you observe and what you constrain, meaning this degenerate combination, right? Now I can change the shape of the triangle, and each of these terms will contribute differently. So I'm going to be able to constrain separately this guy, and this guy, okay? Because as I change the triangle, the contributions of each of these terms is different, so I can actually constrain separately this, and that. In particular, if I constrain this, then I can break the degeneracy that I had at the power spectrum level and get to A, which has the growth factor and the scalar amplitude coming from inflation and so on, okay? So then you can see how non-Gaussianity allows you to break the degeneracies and improve your constraint on cosmological parameters. Does that make sense? Yeah, so the growth factor, remember, when we solve for the equations of motion, we saw that in linear theory, meaning when perturbations are very small, if I calculate the perturbation at time t is the initial time times the growth factor at time t divided by the growth factor at time t0, Okay, so it essentially tells you as perturbations are collapsing, how much they are growing. Okay, in the linear approximation, it's just an overall function of time. And this depends on omega mater, omega lambda, all the cosmological parameters. Yeah. Yes. In fact, the last slide is going to be showing you measurements of the bispectrum in real data, okay? So stay tuned. Yes, you can measure it. Yes. All right? But remember, it has all this physical information about how structures form, right? The spherical collapse, the shift due to a dipole in the mass distribution, right? And then changing shapes due to gravitational tides and so on. And this extra dependence on the triangle shape is coming from the fact that you go from matter to galaxies, and that furthermore can be influenced by spherical, accretion and tides as well. Yeah. Yes.
When you go to Fourier space, the Laplacian becomes like k squared.
Yes.
Doesn't this beta enter in the calculation for the bispectrum at 3 level?
No, at 3 level, no. Yeah, so in the notes, I go through some arguments of it's clear how to order these guys. This is first order, second order, third order. The question is, how do you count this guy, right? It's linear in the fluctuations, but it has a k square, right? And so there are some arguments, which for lack of time, I still have to talk about rational distortions. I won't go into the details, but roughly we are going to count this the same as a cubic order, okay? And you can read why. So if there is time later, I'll explain it at the end. But yeah, but that means because it's cubic order and the bispectrum is only at 3 level, we need quadratic order. It doesn't enter here. Okay, very good question. Yeah. Okay. Okay, so now one loop power spectrum. Okay, so now remember when we did the matter one loop, right? We find that it's linear, and then we have this P22 and P13, okay, which is the one loop correction, right? Which needs quadratic perturbations, and then linear and cubic, right? So now same thing, we are gonna have, obviously, coming from bias alone, we're going to have a quadratic, so this against itself when we do the two-point function, okay? And then linear cubic when we do, again, the two-point function, right? So there are going to be two contributions coming from that. Furthermore, check this out, there is also this against this, right? Linear against quadratic, right? Because remember, these are nonlinear fields. So inside of them, this guy has the F2 kernel, so it has quadratic corrections in the linear fields as well. So you can see now the power spectrum of galaxies will depend on the bispectrum of matter, because it's going to be this against this is the three-point function of matter, which now is not zero, is non-zero because it has evolved, right? It's not about the primordial one. So now you see that when you measure the power spectrum of galaxies, you are also dependent on the non-Gaussianity in the matter generated by gravity, okay? So, so this, as you can imagine, can get, the expressions now are not as simple as a P22 plus a P13 because it will be a P12 because they will involve the bispectrum of the matter, okay? So there are lots more terms, which I'm gonna write schematically in a second. The other thing you have to worry about is when we do, for example, the 1 against the 3, and I briefly mentioned that yesterday, is that when we did the 1-3, I told you briefly that this guy was a bit sensitive to the UV. Okay, it didn't diverge, but it was a bit UV sensitive, right? And there are ways of fixing that using introducing a free parameter, like in EFT, which is precisely a term like this that also comes from bias, okay? The alternative was to include the fact that when there is orbit crossing, you have this Vlasov hierarchy that generates a velocity dispersion tensor, and that cures the UV sensitivity of these guys, right? Now we have a similar situation with bias, because when you do this against this, you will see that, in particular, these two terms give you a divergent. Now it is a divergent contribution. So in order to explain that, let me do it with this guy. Okay, the calculation with this will be the same. Okay. Now this is a perfect example of what Gonzalo was talking about. That when we write, he was writing Lagrangians. I'm writing relations between, matter fields and your tracer. It's just a statement about the symmetries, right? So this was, again, following Gonzalo's words, this was just a device to tell you what are the most general relationships I can write between this guy and this guy based on symmetries alone, right? So when I calculate correlators, which are the observables I'm looking at, right? I should just look at the form of that the terms have. If they have the same form, then I can put them together, okay? And so let's do that with this B3 guy. So now I'm going to calculate B1, B3 over 3 factorial, right? I'm going to do the 2-point function between, or the power spectrum between this guy and this guy, right? So there are two combinations, this against this. When this is K1, this is K2, and vice versa. So there is a factor of 2. And then I'm going to do delta of K for the B1. And because it's just linear is enough, right? Because this one is, I already have 4 deltas. So if they are all linear, that's the leading contribution. So I'm going to call it delta 1. And then I'm going to have delta 1 cubed, right? So a cubed in X space is a convolution in Fourier space. So I have a delta 1 of K1, Q1, sorry, delta 1 of Q2, delta 1 of Q3. And all these guys, all these Y vectors have to add up to K prime. Okay, and now there is an integral here over all the QIs. Okay, so that's the 2-point function between delta linear at K1 and delta linear at K prime cubed, delta linear cubed at K prime. Okay, so that's just a convolution. Okay, and so again, we do the same thing we've been doing for a while now, right? Of pairing, the delta 1 is a Gaussian field, so now I have 3 possible pairs, okay? But they all come the same because this is delta 1 cubed. There is symmetry of exchange. So I have 3 terms. So I have 3 terms, and here I have a 3 factorial and a 2, so I get a 1, okay? And I can just calculate one of the terms, so let's pair this with this. So this gives me a power spectrum of K times these 2 Y vectors by translation invariance add up to 0. So I have a Dirac delta K plus K1. Then I pair these 2. I get a power spectrum of Q2 and a Dirac delta of 2 plus 3. Okay, and finally I have this Dirac delta here. Okay, so now check this out. Okay, Q1 is minus K. So let's count here what I get. I get K prime minus Q1, but that's K. And then minus the sum of Q2, Q3, but this is 0. Okay, so this guy becomes a delta function of K plus K prime, which you better get that, right? Because this is a power spectrum. It has to be translation invariant between the 2 external guys, so it has to be diagonal. So this is now the overall Dirac delta, right? So that killed, so this kills one of the Q1 integrals, right? And the other integral, I kill it by setting Q3 equals to minus Q2, so I only have to do one integral. This guy comes out, P of K. I still have B1, B3. And then I'm left with the integral over Q2 of P of K2. And now you see, this is the integral. Now let me write it D3Q here. So it's a dummy variable. So remember, this power spectrum decreases as k to the minus 3, so this diverges logarithmically. Okay, so this is the unsmooth variance of the density field. So this diverges logarithmically, but you can see that this whole thing is just has the same symmetries as the linear bias, right? It's the linear power times something, right? So it's exactly the same symmetries I had as in the linear bias. So I can absorb this coefficient into there because, again, that was a statement about the symmetries. This guy and this guy have the same symmetries. That's it. All I need is a constant times the linear power. So this term against this doesn't add anything new that this against itself. Okay? You can show the same thing happens with this against that. Okay? And you can show that if you do this against that, you actually get 0. Okay? So at the end, the only thing that comes from cubic order is this guy. Okay? So after all that, we can write the power spectrum to one loop in terms of observables. So it will be the leading order term that we already had, and then all the terms. So this is now, I'm not going to write all the expressions because they're very long and not very illuminating. So this term will be when you do this against this, now involves the bispectrum of the density perturbations, okay, with some one-loop integral. And I'm going to call that P of B1, B2, because it goes as B1 times B2. Same thing for the thing with tidal bias. And then we have the 2, all coming from quadratic bias, the 2 coming from quadratic and tidal bias, the 2 coming from tidal bias with itself. Finally, the 1, 3 coming from cubic bias with linear bias. And then finally, a coefficient which is coming from considering that this is a third order term. Now I correlate with this guy. I get the power spectrum, but with a coefficient with a k squared in front. So this will be minus 2 beta now, k squared times p delta delta. So you can see this is the thing that we worked out that depends only on gravity. This guy now will depend on the bispectrum from gravitational evolution, right? And these other guys, they are all coming from bias, from the bias relation. Okay, so you can see that depends on at least they have one power of the quadratic or cubic bias. So you can see something that was pretty simple at 3 level, now it became a lot more involved. Okay, and I'm going to show you how well these things work when you look at simulations in a minute. Now, there is one more step that we still have to do. Yes. You have a question? No. No, you were stretching. Yeah, I do that all the time. Good. There is one more step we have to do. So this is the deterministic relationship, right? You can see there is no stochasticity here. There is another contribution which is stochastic to the formations of objects, which depend on the small scale modes, precisely where this galaxy forms compared to this one. It lives in a slightly different region, so there is some stochastic noise. okay? And that also happens in particular for discrete objects like galaxies or any other discrete thing. Everything I'm doing here, I've been always assuming everything is continuous field, right? But galaxies, there is one there, next to it, and maybe nothing, right? It's not like a continuous matter field, which also is not continuous, and maybe discrete particles, right? So this is what we call noise terms. So there's also a stochastic component to this bias relation. And you can show for the bispectrum is the same as if you have Poisson fluctuations, only with free amplitudes. So the noise that you need for the bispectrum is to add the same noise you will have if you have Poisson fluctuations. So you have true new free parameters, epsilon 0 and eta naught, nothing to do with the slow roll parameters. Okay, and for the power spectrum, because we are going to one loop, so that it will be a constant noise term, which will be the same thing. It will happen if you have Poisson fluctuations, but with a free amplitude and 0. And then you need to go one more order in the derivative expansion. So there is also a k-square. So you see now the fact that you have stochasticity, that the bias relation is not exactly deterministic, adds more free parameters. Okay? But that's life. Always the rule of the game is to write the most general thing that accounts for all the symmetries. Okay? So you cannot go wrong with that at large scales. Whatever is the process of galaxy formation, which we don't understand fully, as complicated as you want, okay? Just throw anything. Just make up whatever you like. At large scales, it has to look like this. That's the beauty of this. Okay? So next week, when Paco is going to do a completely different approach, right, based on simulations, simulations-based inference, machine learning, and so on. That's complementary to this in several aspects. One of it is it's not based on the perturbative expansion, so it has the advantage that by using simulations, you can go to smaller scales. Using these machine learning techniques, also, you will have lots of more free parameters. The disadvantage, I would claim, is that it's hard to make these algorithms, or not impossible, hopefully, it will be done at some point to satisfy all the symmetries. And it's also not clear that the number of parameters that they are adding, which is huge, it's really the most general one. Because once you lose this hierarchy that you have at large scales between the magnitude of each of these terms, it's hard to know what to add and how many to add and so on. So it becomes difficult to justify from first principles. But of course, it's very interesting, and you may get more information, of course, by going to smaller scales. So you're going to see a completely different approach next week about this. All right. Are there any more questions about this? I'm going to switch to Rashi space distortions. Okay? All right. So what are these Rashi space distortions? So now we are going to talk about how we observe in galaxy redshift surveys. So in galaxy redshift surveys, what we do is we look at galaxies, right, through the telescope. We identify spectral lines, and we measure their redshifts and the two angles on the sky. Okay? So examples of these are, SDSS, BOSS, DESI, Euclid. Sorry if I'm leaving out your favorite one. So we have angles on the sky plus redshifts. And from there, we would like to get the comoving positions, right? Everything I said here starts from having things in comoving space, right? Unfortunately, galaxies don't come with a flag that says, I'm here, you know, at x equals blah, blah, blah. It comes with a redshift, if you're lucky, and you can measure the redshifts. Now, in a smooth universe, this will work perfectly fine, right? So in a smooth universe, if there were no fluctuations, right, we have the recession velocity is just up to a Hubble constant. It's just the physical position r, or if we want the comoving position, we just divide by a. And that's our old friend, the comoving Hubble or conformal Hubble curly h. Okay? So now, of course, the whole point of these lectures is that we have fluctuations. Therefore, the velocities that are creating these redshifts are, there is one component, of course, which is the expansion of the universe. But there is also a component which is the velocity field that we've been talking about for the last few days, right? So that means that when we divide to make what would be the comoving position in a smooth universe, we are going to get a different coordinate, which we call the redshift space coordinate. Comoving coordinate, which will be the correct one, right? So I'm here using that the velocity that we measure is actually contribution, that is the velocity field due to perturbations. We will have a new contribution, which is this in units of curly h, dotted into the line of sight, right? Because the redshift is coming from the line of sight velocities, right? The only contribution is coming from the recession velocity, which is along the line of sight. And this contamination, of course, happens only along the line of sight. Okay? So that means that when we place galaxies in their moving positions by dividing by curly h, right, by using the redshifts, then we get a contamination from the true position due to the fact that we have peculiar velocities. Now, here is where we are going to use the technology that we already developed. Let me remind you, this velocity field I can write as curly h f times velocity u that has now units of distance instead of kilometers per second, right? Because I'm factoring out Hubble. I remember the divergence of this u is this capital theta that we talked about when we solved the equations of motion. And remember, this capital theta is equal to delta in linear perturbation theory, for the most growing mode and so on. And this f here is the growth rate, which has useful cosmological information here, omega mater, omega lambda, etc. Okay? And remember, we're going to assume the velocity field is irrotational. So it only has a scalar mode, no vorticity, which is an excellent approximation for the scales we are working at. Okay? So that means that we can write, you can see here, what enters is the peculiar velocity in units of curly h. So what is going to enter is minus f, which is what we are after, times this velocity, which has units of megaparsecs distances. Okay? So we can write this, that relationship in terms of this u velocity. And E hat is LOS, means the unit vector along the line of sight, okay? So you see, this guy has to have units of distance. This guy is dimensionless, everything else is dimensionless, and this is, of course, this it has units of distance. You can see here my screw up with arrows. This arrow means exactly the same as this arrow. I keep doing that by now. Hopefully, you guys are used to this. Okay, now, here's the deal, okay? So we are observers, right? We are looking at some galaxies, right? And so now we are observing these galaxies along the line of sight. The line of sight is the radial direction away from the observer, right? And now you see the redshift space positions will be the true positions at, you know, when we are looking perpendicular to the line of sight, right? So if this is the line of sight, distance is perpendicular to it will be correct because this is 0, but parallel will not be correct. So now you start to see, when we talked about symmetries, this is going to break the isotropy because clustering along the line of sight is contaminated by peculiar velocities. Perpendicular to the line of sight is not. So it's going to create some anisotropy of galaxy clustering as you move from parallel to the line of sight to perpendicular, okay? Furthermore, there is a special place in the universe, which is where we are located, right? Because you see, this radial vector points towards us, right? So that means that it's also breaking statistical homogeneity. So here you see an example where the two symmetries we've been using are broken, but it's nothing fundamental. It's just the way we observe things, right? The fact that we cannot disentangle the peculiar velocities from the expansion of the universe. Now, happily, we can get away from one of them because most of the time, the survey is very, very far away compared to us. So that means that this line of sight vector is almost parallel, okay? So that means we can take this line of sight vector to be fixed, and let's call that the z direction. So let's assume this is the z unit vector, right? So in that case, which corresponds to taking the observer and putting it at infinity, right? These distortions are going to happen only along the z-axis and not perpendicular to it. Then there is no loss of statistical homogeneity because now the observer is at infinity, right? But we still have anisotropy. We cannot get away from that. Now, this is called the plane parallel approximation of the infinite observer distance or whatever, blah, blah, blah. So that means in this approximation, which I'm going to take from now on, we still have statistical homogeneity, so statistical translation invariance. Still, the correlators will have to have Dirac deltas in them. But these guys now will not be isotropic, okay? And they will depend. The anisotropy will depend on this parameter f. If f is 0, then will be isotropic, right? So that means these anisotropies of correlation functions are going to have information on the thing that we want, okay? So that's pretty cool, okay? Now, in this approximation, now this means this mapping becomes very simple. It becomes like this, where now we just care about the z direction of this velocity u, okay? So this is what we call the RSD map, redshift space distortion map. Okay, so the map from X to S. Any questions so far? Okay. All right, let's see what we can do now. So this is one of the easiest of the three things we discuss. Just to give an idea, it's the easiest thing to derive. The expressions look innocent enough, okay, compared to bias and nonlinear evolution. We'll see this is also a nonlinear map. is the easiest to derive, is the easiest to look at the equations, is the harder to predict of all of them, okay? So it's the one that actually limits how far into the nonlinear regime we can go, much more than bias and nonlinear evolution of matter. And you'll see why, hopefully. We're running out of time, I'm running, okay. We'll see what I can do. Still have the slides, but I'll do my best. So let's derive it, and then I'll probably have to cut some derivations, and you can read them there. So now what I want to do is, okay, we have this map, right? What does this tell us about the density perturbations we measure in Redshift space, right? Now, all this map is doing is just moving galaxies according to the line of sight velocities, right? So it conserves the number of galaxies, right? Or if we are thinking about matter instead of galaxies, it conserves mass, right? It moves mass around, but it doesn't create nor destroy mass, okay? So that means there is a conservation. So if I write now the density in Redshift space, okay, is 1 plus the density fluctuation. So this, I'm always, the mean density is always out, okay? Doesn't matter. The mean density is, of course, also conserved, okay? So 1 plus, this is the density perturbation times its volume in Redshift space must match what I had in through space. Okay, so that's a very simple relation. And from here, we can derive everything, okay? So that's what I was saying. This is like a very simple thing to understand. In particular, we want to calculate the power spectrum and so on. So all I need to do is I want to Fourier transform this guy, right? Now, this guy already has its integral measure ready to go, okay? So in order to make a Fourier transformation, I just multiply by a plane wave. So I have to multiply here by the same thing, of course. Okay? Then, okay, following my notation for Fourier transforms, I need to divide by this. And then I integrate. Okay? So the first term gives me Dirac delta. The second term gives me what I want in Fourier space. Okay? And now on the right-hand side, the integral is over x. And now I can break this plane wave into the plane wave in real space, plus the other component here coming from this guy. Okay, so I write this inside the plane wave that I have on the right-hand side. So this gives me e to the I f kz uz x times 1 plus delta. Is that clear? Okay? Now I can put this Dirac delta on the other side. The integral of this alone is a Dirac delta, so I can just do this minus 1. And there you have it. The Redshift space density Fourier modes, okay, are the density is the standard Fourier modes, okay, which will be Fourier transform, times a phase here that depends on the velocity field, okay, and depends on the wave vector along the line of sight. Okay, so notice, if I set f equal to 0, right, this phase is 1, 1 plus delta minus 1 is delta, and this will just be the standard Fourier transform over in real space, okay? So you see now we have a mapping from density and velocities along the line of sight to the observed Fourier mode, okay? Now, because I'm running out of time, I'm going to rewrite an alternative expression which I derive in the notes. So I'm going to call this IFKZ because it appears all the time as lambda. So I'm going to write it. And remember, this delta could be galaxies, okay? So I can put here a delta G, just to emphasize there are galaxies. And you can show, or you can look at the notes. You can write this in that way as well, okay? So see the notes for this. Again, this term also depends on the gradient of the velocity field, okay? So, so now we are going to look at this in two limits to understand what are these redshift distortions doing, okay? The first limit is when this phase is very small, of course, okay? So this phase, limit 1, is when this is, remember lambda is purely imaginary, right? So when that is much smaller than 1, that will happen when lambda goes to 0, which means I'm looking at low K modes, right? At large scales, right? So this is the large scale limit. Now, what's the physical interpretation of this, right? Is I can write this as FUC in magnitude, right? Much smaller than 1 over Kz. And 1 over Kz is the characteristic length of the perturbation that I'm looking at, okay? So this is saying I'm looking at some perturbation, and the redshift space displacements are small compared to the wavelength of the perturbation I'm looking at, okay? So displacements from the RSD map much smaller than the characteristic length of the perturbation, okay? So in that limit, of course, this exponential I can set to 1, right? And then you see I get the true Fourier modes plus a contribution, which is this guy. But this guy in linear theory, remember, its divergence is precisely delta, okay? And this is one of the contributions to the divergence. I don't have the x component and the y component, right? But if you Fourier transform, right, a gradient is a gradient in z is kz, and uz will be in kz as well. So you will get kc squared over k squared. That's the cosine of the angle of the k vector with respect to the line of sight squared. So if you do this, you get, in this limit, you will get delta g plus f mu square delta, which is linear bias plus f mu square times delta k. Okay, and mu is kz over k. So for modes which are perfectly aligned with my line of sight, I get an amplification, okay, of the density perturbation that I see in true space. For modes which are perpendicular to the line of sight, which is 0, then I get the true mode, right? Which we already knew, because perpendicular to the line of sight, there's no contamination from velocities, okay? Any questions about this? Okay? So this is known as Kaiser effect, for Nick Kaiser's paper from 87. Okay? And that creates a positive quadruple. Okay? So you can see now the anisotropy. This guy is statistically isotropic because, right, as we discussed, this guy now, the redshift space one, will be statistically anisotropic. Okay? Good. So there is a second. So that means in this regime, you can think of 1 plus f over b1 mu square amplification of the density perturbations. Okay? So that means the power spectrum now will be anisotropic. Or let me, since I'm not going to use this, so let me write it back like that. So the power spectrum now in redshift space is going to be the power spectrum in real space with this anisotropic contribution now squared because it's a 2-point function. And that means now this has up to, it has a monopole, it has a quadrupole, and it has an hexadecapole. So it has 4 multiples here. So usually we write this in terms of Legendre polynomials. Okay, in linear theory, only 4 multiples arise. Once you put back the exponential, all the multiples are generated. And so the monopole is just the spherical average of this. So I'm going to write this is the monopole. Let me write the quadrupole. You can write the hexadecapole. It's in the notes. Okay, so we have now a positive quadrupole. Okay, and you can understand how you generated a positive quadrupole just by looking at the physics of the displacements caused by peculiar velocity. So let me do it quickly. So imagine I'm the observer looking at a single Fourier mode. Remember, in this limit, we are in linear theory. We can analyze Fourier mode by Fourier mode. So this is the Fourier mode in real space. So this will be delta, okay, before I do the mapping, right? And this is the z direction, right? So I'm looking at a mode which has mu equals to 1. So I want to see if I can understand why I get maximum amplification when mu is equal to 1, okay? Now the key here is, how does this match? Here I have an overdensity, right? And here I have an underdensity. What is the velocity field doing, right? The velocity field is doing is this. It's flowing into high density regions and is outflowing from underdense regions. Okay, so this is velocity in units of Hubble. So now it has units of distance, okay? And that's exactly what the velocity is doing, right? If I have an underdense region, this is velocities outflowing from here. It's being attracted towards here, okay? These guys is being attracted to the next peak. These guys are being attracted to that peak, okay? So that means when this observer adds the expansion of the universe here to the peculiar velocity, it's going to move this matter in this direction, right? And this matter in that direction. So you see what happens, the Redshift space density perturbation, it will be higher here, right? So the density perturbation in Redshift space is going to look like this. Whereas here, the observer is going to subtract the expansion of the universe from the outflow here. So it's going to move matter that way, and matter that way is going to make this underdensity even more underdense. So there you have it. You get an amplification, right? If this was B1, this thing will be B1 plus F, okay? For mu equals 1, which is what we have here. Is that clear? Okay? So there you have it. Redshift space distortions at large scales, when displacements are small compared to the characteristic size, will increase the density perturbation along the line of sight. You can also think of it if an observer is looking at a spherical perturbation now. So now I have inflow. Imagine now a spherical perturbation. The velocity field will look like this, right? There is a high density region here, right? Once I do the mapping, right, this is going to add to the expansion of the universe from this observer's point of view. So it's going to squash it that way. This one is going to move it that way. This one remains untouched. So when I look at this spherical perturbation in Redshift space, it's going to look like this. So I get a squashing along the line of sight, and that means I enhance the perturbation along the line of sight, which is precisely what I have here. Okay? So now let's look at the opposite limit.
Sorry, so basically, if you are looking, for example, to collision of galaxies in space, right? What you will see is like where there is galaxies, you will see like more galaxies than
No, the total number of galaxies is conserved. Just their locations is changed.
yeah, but there will be like split on this.
They will be bunched up, yeah, on high density regions, they will be closer. In this regime, right, at large scales, right? At large scales, right? Right? So imagine this is like 100 megaparsec wavelength, right? And this displacement is very small compared to 100, say it's 1 megaparsec or something. In this limit, yes. Now let's go to the opposite limit and see what happens. In the opposite limit, as the word says, opposite, the opposite happens. Since I'm running out of time, I'm going to only explain it qualitatively. I don't have much time left, unfortunately. But you can see from the expression here. So let's go back to the full expression before I made any approximations. Okay? So let's compare what happens. Now, this phase is going to be large, right? So second case, I'm going to have this much larger than 1, okay? Remember, physically, this means now the displacements are large compared to the size of the perturbation, right? So now these arrows are going to be large compared to the size of the perturbation, right? So let's do it in this picture, okay? Let's do that intuitively now. So now, the way you achieve that is by high lambda, so high k, so we are going to small scales, okay? In particular, we are probing now, we are going into scales which are, say, the size of the virialized system or smaller, right? So now the observer is looking, now my circle here is, say, a dark matter halo or inside a galaxy, say, okay? So now the velocities there are not coherent like you have on large scales because this is a virialized system. After perturbations collapse, remember we're talking about all this orbit crossing, the dark matter particles are doing all these crazy orbits, right? And the size of the velocities, once I divide by Hubble, they are much larger than the size of the object, okay? That's what that statement is. So now my velocities here, drawing, again, V over Hubble, so they are in units of distance. This is the size of my object now, okay? Are large compared to the radius. So I have some random velocities, okay? This is just the velocities in units of Hubble, okay? They are large compared to the size. Before they were small compared to the size. That's exactly the physical meaning of this expression, okay? So now means, remember, only parallel to the line of sight velocities affect things. But now you can see this thing, because the velocities are large compared to the size of the object in redshift space, this is going to be elongated. Okay, because now I'm going to move this guy here, this guy there. This guy is going to move according to the parallel component, right? This guy is going to move here. Is that clear? Okay, so now I'm creating an elongation. So I go from a positive quadrupole to a negative quadrupole, okay? And this is what the people have called as the finger of God effect, because it creates this, makes these virialized systems in true space into fingers in redshift space that point back to the observer. Okay? So if you look at the galaxy redshift surveys, you will see all these fingers that point to where the observer is. Now, how can we understand that picture from this expression? It's actually pretty easy, right? Because when we put this exponential equal to 1 before, this is the Kaiser result, okay? So now that we see this effect now is multiplying the Kaiser result by a highly oscillating function, right? Because lambda, remember, is purely imaginary. So because lambda is very large and purely imaginary, as I integrate, it's going to wash out things parallel to the line of sight now. Okay, because this lambda depends on the angle with respect to the line of sight. And it's largest if you are at mu equals 1. So essentially now, instead of enhancing perturbations along the line of sight, this highly oscillating phase is going to decrease things along the line of sight. And that's why the sign of the quadrupole changes, okay? So I need to move into the picture, so sorry. There is a lot more information in the notes, but let me show you now some results. Any questions about this before I move to the pictures?
So every time you are doing an observation, you have to correct this, right?
Yes, yes. This is it's a very large effect, right? And it actually, yeah, it leaks into very large scales. Yeah, you don't actually need to go into a visualized system to see this, even outside a visualized system. As long as these displacements are large compared to the wave, are comparable to the wavelength, they will happen. Yeah. Okay, let's go into the slides. So this is going to be a summary of all the 5 lectures, okay? With the emphasis on how well these perturbative techniques work, okay? So I'm going to start with this picture. This is a picture of the projection in a simulation, okay? A redshift almost 20, okay? Of what the density perturbations look like, okay? White means high, black means low, okay? So this is to a very good approximation of Gaussian random field. So if I point to arbitrary points here, I should end up counting as many underdense regions as dense regions, okay? As I move forward in time, you will see at the center, I have this, let's see, you can see my arrow here. So at the center, as I move forward in time, you can see the high density region is gonna collapse. And it's gonna make a dark matter halo, okay? So when I say halo, I mean that guy in the center, okay? And you can see now that overdense region in the initial conditions collapses to a small volume, okay? Where now if I look at that void, you see that black thing over there at the end of this guy here, right? They are the expansion of the universe, beats gravity, right? So as time goes on, it becomes bigger. You see that? And so underdense regions, as I was saying, occupy, now if I do a random, without looking, I select different points, most of them will be underdense, okay? And so this is non-Gaussianity, right? So this is this picture that I drew last time. You go from a Gaussian distribution that has symmetry between positive and negative perturbations to this PDF, okay, which is non-Gaussian, and we calculated the skewness and so on. Now, how does this look in practice? Remember I told you in perturbation theory, you calculate the skewness at 3-level in perturbation theory. So these dashed lines are now the predictions of 3-level PT for the third cumulant, the 4th, 5th, 6th, 7th, okay? So there are brave people that calculated this to actually all of them. And the 3-level prediction is the dashed line. And this is at different times, okay? So this is early times, this is late times. So you can see at early times, it works down to smaller scales than at late times when perturbation theory, when fluctuations are larger, so you cannot go past the nonlinear regime. So you see an enhancement there, okay, at small scales, and you can calculate the one-loop correction. You will see you can capture that enhancement up to some small scale. Now, what people have done, this is a very old paper, right? So I'm telling you basically the whole story of the field. What people have done, you can use this 3-level approximation and this 3-level calculation of all the cumulants and sum them up and calculate the probability distribution function, okay? So calculate this guy. Very well, okay? So this is, what happened? It crashed. Oh, because my internet, my NYU thing, no. Okay, there you go. My VPN died somehow. Doesn't matter. Okay, so this is this calculation of the probability distribution function, and you can see this is at some particular time, and then you smooth the field with different radia, so you make it, smoother or less smoother. So if you go to large scales, are 15 megaparsecs, you can see it looks, are these triangles here, it looks more closer to a Gaussian, but it's still not Gaussian. It's not symmetric with respect to 0. As you go to smaller and smaller scales, you can see that it's highly non-Gaussian. And this tree-level resummation of all the tree diagrams that describes all the leading order cumulants works very well compared to simulations. So now this is a movie of formation of structure. As time goes on, you can see going down in redshift, you see what the structure looks like. So the red guys are more massive galaxies, if you wish, and the black guys are smaller ones. And you can see the structure in the universe is this very filamentary, has lots of filamentary regions, okay? And in between filaments, you have these big dark matter halos, as you saw in the first set of slides, okay? And the nice thing about this is that the power spectrum will try to measure is a Fourier transform of the two-point correlation function. So it measures the average distance between pairs in this picture, no matter whether they are like this or like that. So it's averaging over all possible pairs, okay? Now, when you measure three-point function or bispectrum, now you are sensitive to the shape of structures because you have 3 points. I can put the 3 points in an equilateral triangle. I can put them in a flat triangle, or I can put it in a squeezed triangle. And how many of the galaxies or whatever you're looking at happen to align in these configurations will allow you to test what's the shape of structures generated by gravitational instability. That's why this F2 kernel was sensitive to the tidal field, right? It's not just the spherical collapse that is going on, it's also the shift, how structures move, how they are affected by tidal fields, and this will create a sensitivity which will test what kind of shapes gravity creates as it evolves. Okay, so if I now this movie is showing the formation of more massive things eventually forming a cluster. So you see the box size now is 40 megaparsecs, and you see how it's collapsing and forming a big guy there, okay? A dark matter halo with a big, it's a big cluster of galaxies there in the middle. And this is how many objects you get as a function of time. This is the so-called mass function, low mass, high mass, and the abundance. You can see as time goes on, you're getting more and more of these guys, okay? This is something people are very interested in. As time goes on, you form more massive objects going up to the 10 to the 15 solar masses. Okay, so now let's concentrate on the non-Gaussianity, okay? So if I show you these 2 pictures, you say, well, I just told you about the shape of structures generated by gravity, right? You will probably agree that the picture on the left and the picture on the right has very different physics, it looks like, okay? So the one on the left, I ran a simulation, okay? So it should look similar to the one before. This one I did a Rayleigh-Levy random walk, okay? Some totally no physics whatsoever. It's just a random jumping of particles, okay? So you see it looks very different. Now, after my patience of making the second picture, if you measure the two-point function or the power spectrum, you will get exactly the same answer, okay? So this is telling you up to my patience of making these 2 measurements the same and changing the random walk a little bit. You can see that the difference between these 2 pictures is basically all in their non-Gaussianity, okay? So you can measure the power spectrum. One is the red, the other is the blue. They agree, okay? Up to my patience. So now let's go to the real thing. So this I already mentioned. So the linear power spectrum after inflation and radiation era has this shape. Okay, so now I put the logarithm, but basically it's the same thing. So we have inflationary spectrum approximately scale invariant, this peak having to do with the size of the universe and matter radiation equality, the baryon acoustic oscillations, and this radiation suppression. Now, this is what the field has developed over many, many years of working very hard, and this is what we observe with different tracers. So you can now tried to put all the tracers we see here. Is an incomplete list from maybe almost 10 years ago, probably. Okay. You can see we have here the temperature part of the CMB, okay? The E-polarization, the reconstruction of the gravitational potential along the line of sight from CMB lensing, okay? Then we have these lone luminous red galaxies, okay? You can see now probes more into the BAO regime, okay? And a bit lower. Then we have the Lyman alpha forest, which I didn't discuss, but it's just the essentially neutral hydrogen along the line of sight. We also have from gravitational lensing some results from DES, year 1. And you can see this shape, this reconstruction of the linear spectrum, okay? Everybody is more or less getting the same answer, okay? So this is not just a pipe dream. You can actually... so now let's move into perturbation theory a bit more. So I mentioned yesterday calculations of EFT and this Blasov equation. So now we are doing here is some toy models where we take a scale-free power spectrum and we actually make it as blue as possible. Okay, so without the effects of radiation error to exaggerate these UV sensitivities. And you can see this Blasov predict. So this is to make it really, really blue. This will be scale invariant all the way if we didn't have the transfer function, okay? And then this is a redder, okay? So as you go bluer and bluer, this effect of the velocity dispersion becomes higher and higher due to this crossing of particles orbits. And this is the ratio of the nonlinear power divided by the linear power, okay? So as I said, you can try to fit this within an EFT by adding a free parameter. You can also do the calculation from the Blasov hierarchy, okay? And you can see in the Blasov hierarchy, because you're solving this Blasov hierarchy, you have more information, so you're doing a little bit better. And this is in response to the question yesterday about the UV sensitivity. So you can see compared to SPT, as you go to high momentum, these perturbation theory kernels get suppressed, okay? So this is what I was explaining yesterday. So let me move on. This is now for a CDM spectrum, so now putting back the transfer function and everything. So this is now a two-loop calculation, okay? So this is a nonlinear spectrum divided by the linear one, so you can see the difference as well. The symbols are the n-body simulation, right? The black line is the standard perturbation theory, which is what I described in this course, okay? And I told you once you go to two-loop, there is this bad boy, this P15, right? And that's what's causing, you see, it's very hard to match the simulations except at very, very low K when you are in very linear scales, okay? As you go to cross into the nonlinear regime, you are way off. Once you include these orbit crossing effects, depending on the size of the dispersion scale, you get in much better agreement with the simulations. Of course, eventually, all bets are off, okay? Okay, so now let's look at the result of bias. So that was nonlinear evolution. So this is now observations. I told you when we write this bias relation, I said, you know, if you work at large scales, this is an ordering of the size of the effects. So if I go to very large scales, I see there is a delta missing in the first term. Sorry, V1 times delta. So that's the term that should dominate, right? And that's what we see, that if delta G should be proportional to delta if I look at large scales. And so that means the power spectrum of galaxies should be proportional to that of the matter at low K. And this is an experimental determination of that. So these are different type of galaxies. In dashed lines is the power spectrum of matter, okay? So these are the BAO, okay? And you can see that different galaxies, okay, of different luminosities are more or less tracing this shape. So if I take, you know, PG divided by P matter, D will be effectively B1 at low K. You can see that these things are flat, okay? So this is saying that, you know, ordering of things that I discussed is more or less correct. So let me move a bit faster. So now let's go into the bispectrum, okay? So you may ask yourself, I only presented the 3-level calculation from bias, but we also have been doing the one-loop calculation. So how well you can improve over a 3-level calculation. So the left panels are how well you predict you can constrain by running an MCMC. Remember, these guys are free parameters, right? How well you can constrain these bias parameters when you look at simulations, when you do just 3-level, versus when you do one loop on the right. So you can see, and adding also the power spectrum, you can see the goodness of fit improves, okay? And you get much better constraints than when you use 3-level, these chi-squares go really horrible. And so one way of visualizing the bispectrum, I have all these triangles. This is a horrible thing to actually show pictures of, okay? So what we are doing here is we are now plotting, contour levels of the amplitude of the bispectrum for ratios of k's, okay? For some particular overall size of the triangle. So you can decompose the bispectrum depends on 3 k's. I can take 2 ratios and an overall average, say, okay? And the overall average are the 3 different panels, and I go here from left is a low k, and then I keep marching into high k, okay? And the way to read these plots is that here I'm looking at equilateral triangle shapes in this corner because the 2 ratios are 1, okay? Here I'm looking at in the left upper corner, I'm looking at squeeze triangles, which are like this. And in the lowest corner, I'm looking at folded triangles, which are like that, okay? And in the middle is somewhere, some arbitrary shape. So now the bottom panel now shows what are the deviations of the predictions from the simulations, okay? So the greener is the color is the relative error is higher in %, okay? So you can see the 3 prediction, particularly as you go to higher k, one loop corrections become important. So you can see here in this corner how things start to look bad. Once I add the loop, so this is, you can see from 3 to loop, how you improve, okay? So now this is the same. Now it's looking at what's the contribution of the loop correction. You can see, of course, it's larger there. Okay, so now this is now showing you the whole thing, which is absolutely horrible. That's why I never showed this plot. You can see there are 5,000 points there, 5,000 triangles, and each of them, there is also a prediction there. And you can see the deviation from the model, once you include loop corrections, is pretty good, okay? Okay, this is a similar thing showing the chi-squares and so on. Okay, since it's already time up, so let me now go to redshift distortions. So this is now showing the 3 multiples, okay? P0, L equals 0, L equals 2, L equals 4, okay? Now, one thing to notice, usually all the plots are in h over megaparsecs. This is 1 over megaparsecs, so it should be divided by little h to convert to the previous units. So 0.2 here is roughly 0.26, almost 0.3, okay? So in the previous units. But you can see the predictions of perturbation theory work very well for the monopole. For the quadrupole, which is this guy, okay? Eventually, you run into some deviations, and the hexadecapole is very hard to measure, but So eventually, as you go to small scales, of course, perturbation theory is not enough. So now let's see how this impacts in cosmological parameter determination. So this is from a paper that you can find on the web. So we have 3 papers, but it's the Eggemeyer 2025 paper. So you run an MCMC, Markov chain Monte Carlo, with all these parameters that we discussed for the bias, and then we are interested in how well we can constrain the cosmological parameters, little h, omega col times h squared, which is this WC, and then the amplitude of the scalar index, okay? And this is for parameters for a survey that is kind of like Euclid-like. So I don't have time to explain all these things. So concentrate on the light blue predictions. Okay, this VDG thing. Okay, so this is showing what is the bias recovering cosmological parameters, the figure of bias, as a function of including more and more modes as you go march into the nonlinear regime. So you want to be, you don't want to have bias in your cosmology. So you see, as you go to the right, depending on the type of galaxy that you're looking at, these galaxies are a lower redshift where you have more nonlinearity. So you can see these guys marching up higher than this. Okay, so this all depends on the type of galaxies. So these are galaxies in the simulations. Okay, this is the goodness of fit or the chi-square, right? So you want to be within these bands. And this is eventually how much is your constraining power, okay? But you shouldn't use constraining power high when the model is biased, okay? Because you're getting a very good constraint, a very good wrong constraint, okay? And you can see here in each cosmological parameter, as I increase and I go to march into the nonlinear regime, you can see how things start to deviate, right? Even for this blue thing, okay, it's going to move away, and you're going to eventually get the wrong answer on cosmology. Okay, so this is how we test perturbation theory against simulations to actually check up to what scales we can use them. And here is again now showing how you break the generacies when you add bispectrum information. So light blue is power only, then adding bispectrum, and you can see how you decrease the error bars on, say, cosmological parameters substantially once you add the bispectrum, okay? So you're using this non-Gaussianity to constrain cosmology on top of the power spectrum alone. So again, this is again showing, so this is probably one of the last slides. So you, again, concentrate on the light blue. You can see for each cosmological parameter, this is Hubble, this is omega cold, and this is the amplitude of the scalar spectral index. As you add bispectrum, the bispectrum is also anisotropic in Roche space. So we go from here to adding bispectrum monopole, okay? And then adding on top of it the quadrupole, so we gain 23% better, 23% better constraints, okay? And as you do the same, so these are, again, the top row is for one type of galaxies, the lower row is for a different one. So you can see as you add bispectrum information, when you add the monopole, you get a lot of constraining power on little h and omega cold. When you add the, I want to use the arrow. When you add the quadrupole of the bispectrum, you also get a higher constraining power on the of the amplitude of the scalar amplitude AS. So last pictures. So now, if I put everything together, this is the bispectrum prediction monopole for a particular survey for BOSS, okay? In, again, the same shape as I was doing before. So this is equilateral triangles. These are triangles which are folded, and here is squeezed. This is high amplitude. This is low amplitude, okay? So this is, again, saying low amplitude for equilaterals, high amplitude for these guys is because you saw all these filaments, right, when I show you. So there is higher probability of structures like this generated by gravity than things which are spherical, okay? That's essentially what's going on. This is what you measure. Okay, so this is what I measured some years ago. So you can see, of course, the true data has noise, okay? But you see that the prediction matches what we observed pretty well. Now, if we go to the quadrupole, it's a lot harder to predict and a lot harder to measure. So this is the prediction. This is the measurement. Okay, so this is real life, okay? This is not a simulation. Okay, so you can see that these predictions, are useful to capture what's going on in the real universe. Okay? All right, I'll stop there. Thank you for your patience.
First row.
Roman, sorry, I didn't understand something. In the short scale regime, why should redshift affect the shape? I mean, if it's close enough.
Well,
then-
we are always, no, short scales doesn't mean that it's close to us.
Ah, okay, okay.
It means that the separation between the 2 points that you're looking is small.
Okay, okay.
Yeah.
Thanks.
Yeah, remember here what I'm doing is comparing the shifts to the size of the object. So it's the size, of the perturbation.
Yeah, thanks, Professor. I mean, just as you can distinguish between different regions of the power spectrum per se to infer what's going on physically, I'd like to for you to expand a little bit more on this prediction of the bispectrum. I mean, what does it mean for it to have a preference for a squeezed triangle shapes? You mentioned something at the end there that's it's not favoring spherical collapse. I mean, what can we infer physically from this picture of the bispectrum?
Yeah, so remember when we wrote this F2 kernel and I separated the 3 contributions, right? That is telling you the physics of gravitational clustering, right? There is a spherical piece, there is a shift, and there is a quadrupole, right? Yeah. And so when you translate that in what is that underline is telling, that structure is telling you that if you look at when this sum is maximum and what is minimum, right? It's minimum for this kind of triangles, or it's maximum for triangles of 0 area, essentially, right? And visually, that's what you see. You see all these filaments, right? When I was showing.
So it's directly related to the picture of the filament.
Yeah, the first picture that I show. Well, maybe this picture. Sorry. The picture on the left, which is a real picture, okay? Not this bogus random walk. Yeah. But it tells you, like I was making the point here, with the power spectrum, you can get fooled, right? You may not be able to tell the difference between these two.
Thanks a lot.
Thanks for the lecture. In redshift space distortions, when we have a galaxy at higher redshift, its effect on RSDs gets lower or not? I think I read that it's like the same effect.
Well, it depends, but yes. You notice what is going on here, so it depends on the size of this guy, right? So when we looked at things in real space, right, for density perturbations, it goes as the growth factor, right? The density perturbation times the primordial value, okay? Now velocities, right? Sorry, V now goes as F times D plus, right? And remember F, so this guy looks like this, right? D plus as a function of time, right? It goes something like this. Eventually flattens because you're lambda dominated and nothing doesn't grow anymore, right? But this guy is the log derivative of this with respect to A, so I can put here even A. So you can see F becomes large here, the slope, and small here. So if you plot FD, it does something like this. Well, yes, something like that. It picks a redshift at half, more or less. So we are redshift 0, okay? So that means that everything, if you keep everything else fixed, this is sort of maximum at redshift around the half, okay? So the true nonlinearities in real space are, of course, largest at redshift 0, but this map is most nonlinear at around redshift of a half. So that's what I said, this is the nastiest guy, not only because of this finger of God effect, is because the size, the strength of the map is actually in the middle of what we observe, more or less. So it's not that by going to redshift 1, you're getting a lot better than at redshift 0. You are getting a lot better on the real space nonlinearities, but the redshift space distortions are more or less the same, because we are exploring this region here.
Okay, so I think we can thank Roman for a very good set of that.